Hey, welcome back. I have to turn this vent screw here. It's turned out of aluminium and it has a sealing taper here and an M8 by 0.75 millimeter fine pitch thread here. And to keep it all nice and concentric, I want to single point thread this fine thread. So let's go to the lathe and set it for the correct pitch. That's the feed gearbox of the lathe. I have turning feet for lengthwise, and if you take it multiplied by 0.5, it's the facing feet. We have metric and we have imperial threads per inch. We were interested in metric, of course. And let's see, we have 0.35, 4.5, 0.6, 0.7, 0.8. Dang it, there is no 0.75 millimeter pitch on this machine that we can turn, which is quite annoying. I've seen it on a lot of machines that one pitch is always missing. So let's see what we can do. Okay, that's the chart for threading odd numbered threads. Metric module for metric worms, diametrical pitch for imperial worms, and additional imperial threads. Today we want to cut a metric fine thread. There it is, 0.75. We need to add an additional set of gears, 40 and 80 as a combination gear, and we need a 95 tooth gear in addition. So we need 95, 80 and 40. I do not have those. I have the 90, I have the 30, and I have a 127 and a 120 for metric imperial conversion. So, dang it. Seems like we have to make a bunch of gears. This is phenolic, linen reinforced phenolic. It's an interesting material. You can get it in sheet form and you can get it in round material. If you get the sheet material, it's layer after layer of linen put on top of each other, and it creates a very robust, very solid plate, which is very strong in XY direction if you look top down on it, but in C direction it's less robust because it can delaminate. If you get the round stock, which I do not have here, it's wound up. It's like taking a piece of cloth and rolling it up like this to create something that almost looks like a tree trunk. Gears are made out of plate material. If you use the round material, the rolled material, the layers are right at the teeth. Let's do a quick sketch. If you have your rolled material, it has almost like a grain that goes like this. And now imagine that you put in gear teeth like this. Then you have these layers going through the teeth. That means the teeth will break at the layer intersection. These are two of the Emco change gears. These are made out of cast iron, hence the cast look here. And the phenolic I have is the same thickness. This is a 10 millimeter phenolic, and these change gears are also 10 millimeters. I have a full set of Module 1 gear cutters. You need a full set because depending on the number of teeth of a gear, the shape of the teeth change a little bit. And with a full set, you can span everything from something like 12 teeth at a minimum up to an infinite number of teeth, which would be a rack, a linear gear. And these are Module 1 because the gear cutter here fits. So now we figure out how to cut these gears. Okay, here we find everything for a standard spur gear that we need. First and foremost, our interest is DA, which is the most outer diameter, because we need to turn these blanks down to the diameter so we can cut the teeth. And where is it? dA is module, which is in our case 1, multiplied by number of teeth, C, plus 2. In our case, it's we have 40. Oh, sorry, we're English here. 40 teeth, 80 teeth, and 95 teeth. Module 1, so we can ignore this here. So we just have to take number of teeth plus 2. So this is 42 millimeter diameter. This is 82 millimeter diameter, and this is 97 millimeter in diameter. These are the diameters we're going to prepare, and we need a 19 millimeter bore in them, along with a 4 millimeter keyway. I've never tried key slotting the phenolic. I will probably do a fake keyway. After we drilled the 90 millimeter through hole, I will mill a keyway in here with a 4 millimeter end mill. I suspect that when we try to broach this or slot it with a slotting cutter, we will get a lot of blowout down the backside, and we don't want that. Okay, we're over at the milling machine, and I have a large parallel here. 2 1-2-3 blocks. I will drop my part on top of it and use 2 of these cantilevered clamps, which a lot of people ask where I get these from. These are sold through Hoffman Group and are super high quality, very nicely made with a trapezoidal screw instead of a normal screw thread that's 60 degrees. I just marked the rough center here with a felt marker, and I'm aligning my drill here. I take the drill out and replace it with an 18 millimeter rotor broach, core drill or annular cutter or whatever. In most plastics you have to be a little bit careful with these drills because they tend to grab. So we will use the fine feed of the quill, not the quill handle. Running relatively slow so we do not stir up a ton of dust, and I'm going to use shop vac. There we go. Usually the slug falls out without an ejector pin, but the phenolic is a little bit weird in that regard and does not want to fall out because it tends to get a little bit compressed during the cut, and after the cut it expands and it jams itself in. Could be worse. Punk. And back in. There we go. Now we switch to a boring head and bore it to 19 millimeters. CCMT boring bar with a razor sharp polished insert for aluminium. Okay, there we go. 18 millimeters. Now we can adjust our cut. 10, let's go to 50, measure, and then take a final cut. Should be possible to cut this in 1 or 2 passes to final dimension. Cutting pressure in phenolic is not crazy high with a free cutting tool like this. Running at 580 RPM. In this case I'm able to sneak the 2-point internal mic around the boring bar so it clears, which is very convenient. Otherwise I would use telescoping gauges. In this case the 2-point ID mic is okay. This is 18.35 millimeters. So we adjust by 0.5, 0.1, and then 0.5 and 0.2. This should give us 1902 millimeters diameter, hopefully. I switched to 1000 RPM just to have it cut a little bit freer. Yeah. That was easy. 1902, just the dimension I set it to. I really like the wool hop deburring head. We will not disturb the setting because when I do the next two, I will not have to do any adjustment. I will just put the boring head in, take my cut, and it's done. Should be on final dimension. Boring bar deflection in this material at this RPM and this depth of cut should be small enough not to be a problem. Now we need a 4mm carbide emblem and we will cut the keyway right away. There is a 4mm keyway, quick and dirty. Okay, over at the lathe, and I have a straight shanked arbor. This has a 20mm shank and a 16mm diameter here, and a fine thread here for a nut to clamp whatever you put on here securely in place. And to accommodate for different diameters, I make these bushings out of whatever I have at hand. This is 16mm ID and 19 OD. This slips right over here, and then you indicate it in. Use the set through feature of the 6-jaw to get it on center, or you have a 4-jaw independent chuck, and that you can use that to true it up, but I prefer the 6-jaw for most work. And then the work slips right over. Now I just need a spacer ring to fill up this gap here. This 22mm ring of a mill arbor will do. Of course, this has a little bit of side play, so I'm just rough aligning it so it kind of runs true-ish. Same for the washer. Ugh. Just so it doesn't introduce a whole lot of imbalance. We're not running this at warp 9 anyway, so it should be fine. Turning tool wise, I'm going to use again, aluminium insert. When I say aluminium insert, it's of course a carbide insert, just the geometry for aluminium. Get my tool here. The dust from the phenolic is anything but healthy, so I'm definitely going to use dust extraction to catch most of it. As you can see, the larger chips still flow by. I'm not worried about these. I'm worried about the fine dust that settles in your lungs and on every surface in the shop. It's 20 microns oversize. Should be okay. Should be definitely okay, because on the change gears you set the gear mesh manually anyway. So that one comes off. Spacer rings come off, and our gear blank comes off too. There we go, first one. We're over at the milling machine. I have my rotary table with indexing plates, and I have a 16mm standard mill arbor here in the Morse taper 2 socket, and I'm using the same 16-20mm bushing that I used before on my lathe arbor here on this mill arbor, and I put the phenolic blank over it. I used a bunch of spacers and the M8 screw to pull everything together. Check the runout, perfectly fine, well within 20 microns. And I already selected the correct gear cutter. This is a number 6 module 1, number 6 because going by a chart, number 6 is suitable for 35 to 54 teeth, and this is a 40 teeth gear, so we're right in it. I have a gauge block stack. This represents the center height of my rotary table. That's a dimension I just know. This cutter is 4mm wide, so putting the cutter on center will be a fairly simple affair. I'm just going to drop this on here like this until I make contact, zero out my quill DRO, remove the gauge block stack, drop down additional 2mm and lock my quill. And that's my position, my center height, the cutter at center height of axis of rotation of my rotary table. Next we'll have to touch off on the diameter. There we go, touched off, Y direction 0. This is the calculation for the indexing plate. The rotary table is 90:1 and I want 40 teeth. So we try to reduce the lower number to a number that I have an indexing plate for. That's in my case 20. So 40 divided by 2 is 20. Then we have to divide 90 by 2. We end up with 45. We have to go 45 holes on a 20 hole indexing plate for each tooth. That goes down to 2 full revolutions plus 5 holes. I did a test cut with 3 teeth now, and you already can see the fine dust produced by this material, so we're definitely going to use dust extraction for this too. I'm too young to ruin my lungs, and even if you're old, you're too old to ruin your lungs. Okay, we went one time full around and we didn't end up with half a teeth left or addition. Looking good. So now we can pull this gear off here and see how it meshes. Here you can see the blowout from the cutter where it created this fuzzy burr. We'll get rid of this later. Here's the gear. This is the original 120 teeth gear of my lathe, and this feels good. I'm not worried. So I'll pull this off, and you can see the actual stack up of these parts. A little bit longer screw would be nice. That was a little bit little small engagement length. Now we can pull off the gear. And here is again, this is a 16mm arbor and this is the 16-20mm bushing I was talking about. Looks like a gear to me. Got all 3 gears cut. This is the 95 teeth one, and as you saw, it also came out with no half teeth extra, so good sign. Let's take it off and deburr it. Found a good way to deburr them relatively quick. A small wire brush, steel wire brush, works very well for deburring. I'm using it in the flex shaft handpiece because this has a lot of low speed torque compared to my small electric die grinder. So just turning it around like this and keeping it in contact. The remaining work will be done with a small diamond point in the pneumatic die grinder, and I will just follow the contour of the gear with it. That will put a nice small chamfer on each of the teeth. In the last video somebody asked what this die grinder is. This is a BX pneumatic die grinder, 60,000 RPM. Really a nice tool, but it takes a ton of air. I'm using a teardrop shape, and when I put this in a gap between 2 of the teeth, it starts out here on the larger diameter of the teardrop shape, and when I pull it towards me, it automatically moves down the sides of the teeth and puts a nice chamfer on it until when it hits the bottom of the teeth here, then I can fully get out, and it even puts a small radius on here. So that's a very fast way to deburr these wheels, and put a nice chamfer on them. Little jump forward in time. I made a few parts offline because I want to get them done, and filming takes about 3 times as long for everything. So I needed another axle and sleeve for the change gears, because when you do non-standard threads on the Emco, you need an additional gear. So I duplicated the original one. Everything here is 42 chromoly, pre-hardened, heat-treated steel, which makes it very durable. Everything's just turned. Shaft with lubrication, one grease fitting here. This goes on here. Then you have this washer and the nut. With the square nut, it bolts to the banjo, to the change gear banjo. Then you put your change gears on, 2 at a time. They're of course keyed onto the shaft. And then you take your finely knurled fine thread nut here and secure the gears to the sleeve. And once you tighten this down, the sleeve is still free to rotate. It has about 0.1 millimeter of end play, so it spins freely on the axle and does not bind up and create a very entertaining situation. So this is the new change gear bolt with the phenolic change gear, so let's mount it on the lathe. I think we can do this whole setup with one 30 millimeter wrench. First we disengage the change gear banjo. Go by opening this one nut down here. Then we take off the change gears from this one bolt here. Move this one out of the way. And we take our second change gear bolt and we mount it to this lower slot here. Get the square nut behind it and we thread this together. Just like this. And we move it all the way out so we have room to work. Now we need a 40 teeth gear. This will make contact with this 90 teeth here. Get our gear meshing nice and there we go. A lot of people use a strip of paper between the teeth to get the gear mesh right, but usually this is fine. Ugh. Yeah, these phenolic gears will look like we'll get a nice covering in grease after a few rotations. Now we can add on the 80 teeth gear. There we go. Now we need a 95 gear that meshes with this one. The problem is, it doesn't work because we need a spacer behind it. So I think we can use just one of the spare gears here as a spacer now. Should work out if we can clear the belt. There we go. Now we need those two gears to mesh. The two phenolic gears. There we go. And now we need this 95 gear to mesh with this 30 teeth gear up here. But for that we need to swap this gear around, because now it would mesh with this large cast iron gear, which I'm just using as a spacer. Okay, we need a second wrench. So, as annoying as change gears are, the way Emco did it on this machine is reasonably painless. If I can get this gear here off. There we go. So now we drop the spacer behind the gear, like this. Get the gear in place. Washer, screw and nut. Just a screw, not a nut. Mount it. There we go. And now we can swivel the whole change gear banjo in place. Okay, this doesn't work. We need a smaller spacer than this 120 teeth gear here. Dang it. Such a beautiful spacer bushing. There we go. Gear and the nut. Hold it all together. There we go. That meshes nicely. Now we can bring these in contact. There we go. Now we spin it by hand. Okay, that's looking promising. Let's give both of these posts a little bit of lubrication. Let's have it run. Sounds like change gears, not too bad. Looking good. I'm really pleased. Yes, I put a lot of extra work in these gears and the axle and stuff like that, just for a single part. But sooner or later, I will need this additional change gear shaft and the gears anyway. So now is as good time as ever to make it. Now, finally, after cutting the gears, making the axle, I can cut the thread. I prepared the diameter of 8 millimeters. Unfortunately, I do not have a thread gauge, so I'm using a M8 by 0.75 millimeter fine thread nut. Let's see. I already set the lathe for 0.75 millimeter pitch. Okay, I took a first skim pass and I'm checking with a 0.75 millimeter thread gauge, and looks good to me. Let's continue. Get some cutting oil on there. There we go. It's a little bit tight, so I'll take a spring pass. I'm very pleased. That's a nice 0.75 millimeter thread. So now I can, after I finish the thread here, I can continue on turning the OD. This OD here finished. I left this a little bit fat because if I turned it already down to 10 millimeters, the cutting pressure of threading the part would have caused a lot of deflection, possibly. Okay, I think that's it for this project. The making of the change gears and adapting them to the machine was probably the most interesting. The rest of this is plain turning. So let's bring this to an end. Thank you all for watching and see you next time.